as we increase the voltage, the current also increases. The proportionality constant, right? This is a linear equation. I know it's not easy to tell it's linear from looking at the brightness of the bulb, but trust me, it's a linear relationship. And so what we get is, this is a straight line, right? There's a slope thrown in there, and the slope of that line is what we call the resistance of our device. Okay, this is a light bulb, but any resistive device, this relationship holds. And that resistance depends on the thing that we are, running, putting the potential difference across and getting the current to go through, right? The thing with resistance. So what might it depend on? For a wire, what do you think it would depend on? First thing might come to mind? What would affect the resistance of a wire? The type of material, is that what you said? Somebody said that, I'm sure. The type of material, right? Some materials, the charges might be able to move through very easily. Some materials, not so easily. So that would be our resistivity. Okay, that depends on the material. What else might it depend on? Picture a wire, kind of like a pipe. If you're trying to flow water through a pipe, what would make it easier to flow water through? The diameter, right? Same with a wire. So that means we are 1 over, right? Bigger the cross-sectional area of the wire, the smaller the resistance, the easier it is for the electrons to move through it. And one more thing, what would make it harder or easier to flow water through a pipe? The length of the pipe, that's right. Yeah, the longer the pipe, the harder it is to force the water all the way through it. Same here. Okay. So I've thrown in another term here that sounds similar to R. R is resistance. And what does resistance depend on? It depends on the actual thing that we're using, right? Like a wire. Depends on the diameter, the length. It depends on what it's made out of. It depends on all that stuff. Rho is resistivity. That is just a function of the material. If our wire is made out of aluminum, it has a certain resistivity. If it's made out of copper, it has a lower, slightly lower resistivity. Okay? So resistivity is a function of the material. Resistance is the actual wire, right? The dimension. Not just the material, but also the dimensions. Okay? All right, let's go back to this. So we've introduced Ohm's law, V equals IR. We'll use that a lot. And we've talked about current. The fact that the current everywhere in this simple circuit was the same. And the reason it was the same is because these devices were hooked up in series with each other. The current, if the current doesn't get used up, and there are no forks in the road, right? Then all the current that has to be the same everywhere in these two circuits. The blue current, the same everywhere in that circuit. This one is the same everywhere in this circuit. Of course, these are different circuits, right? I1 and I2 are different. But everywhere in one of those circuits, the current's the same. No matter where we measured it, it would be the same in the top circuit or in the bottom circuit. So there are ways that we can hook up circuits where the current is not the same. So let's take a look at parallel resistors. So we've got a battery, and then the current has a choice. It can go through the first light bulb, or it can come over here and go through the second light bulb. Okay, so parallel. Okay. So they're hooked up like that. Right, battery inputs over here. The current has a choice. It can go through the first bulb or the second bulb to get back to the negative terminal of our battery or our power supply. What do you think? Comparing the brightness of these bulbs, what do you conclude about the amount of current through each one? Same. Okay, the same brightness. So they have the same current flowing through them. Okay, so what we have is current. I'm going to call this I1 and this I1, right? So the same current flowing through either bulb. What do you think is flowing through the battery? I1? How much is going through the battery? 2 times I1. You see that? Because there's a choice. There's a split in the road here. There's a fork in the road right here. So the current comes along here, and some of it takes this path, and some takes this path, and then it joins back up and goes back to the end of the negative terminal on the battery. When there's a fork in the road, the current can split and come back together later on. Those are called parallel paths. Okay, parallel paths to get to the other side. So if we have I1 going through each of these, then we're going to have 2 I1 over there and 2 I1 over here. At these junctions, the current can split or come back together. You see that?
So the top right-hand corner,
Yeah.
that is I1?
Yes. It splits at the at this red dot, and so if I were to, so everywhere, right? Because there are no forks in this path, right? So once you get past this point, the current can't change anywhere here, right? Remember, we already said that it's not created or destroyed. It's not used up anywhere in the circuit. So anywhere along here, it's going to be the same until you get to another fork in the road, and then it can change. Until you get to a junction. That's the only place the current can change. So I can write it in here just to make it clear. But right here, it becomes I1, and it's still I1. over there. Matt?
So you said length affects resistance. So how does length play into this?
Okay, good question. Question is length. I said that the length of a wire changes its resistance. Okay, but remember I also said, where are the circuit elements? Here they are, circuit elements. When we draw circuits, we account for all the resistance in symbols that mean there's resistance there. And the wires, the lines that we draw are perfect zero resistance connections. So if I wanted to account, we know that real world wires, that's hard to say, real world wires have some resistance, don't they? They're not perfect conductors. So these wires in my actual circuit over here have a little bit of resistance. But it's very small, and so in my real circuit, it really doesn't affect things compared to the resistance of the light bulbs. And when I draw a circuit, I'm assuming that these lines have no resistance. And so when I draw this, all my resistance is in these two devices here. In fact, I could have just drawn a resistor here instead of trying to make it look like a light bulb. And when I get tired of drawing these little light bulb symbols, I'm going to do that, which is pretty quickly here. But anyway, so these are zero resistance wires except for these two resistors here. And if I really needed to take into account the resistance of the wire, what would I do? I would draw the circuit like this. Here's my first light bulb, and then there's be a R wire 1, and then maybe my other light bulb has a longer path, so I put a R wire 2 over here to account for the resistance in the wires, but these lines are still zero resistance paths. The symbol accounts for the resistance in the wire.